My name's Lindley Johnson. I'm from NASA headquarters. I run the Planetary Defense Coordination Office at NASA headquarters, dealing with the risk of an asteroid impact. So I'm pleased to be here to talk with you at this conference on catastrophic risk. My presentation might be a little different than the others in that my job is mainly about eliminating catastrophic risk, or at least reducing it to a much lower level. So all of us know that now this risk of a asteroid impact or a comet impact, cosmic impact, if you will, has been the subject of many movies from Hollywood over the years. Kind of captures the public imagination about what would happen if Earth were to be impacted by a large asteroid or comet. So it's a staple of the movies, a cinematic catastrophe, but one might think is the catastrophe actually the natural disaster, or is it the movie and the science in the movie? Because they aren't very well, the science isn't very well projected by Hollywood. But here's a few movies over the last few decades that dealt with this subject. There are literally dozens of them. But one I like to point out is one that not as commonly known, the movie Meteor. And this is one of my favorite movies because the protagonist in it is a person that kind of plays the role that I am in now was Sean Connery. This is particularly timely right now with his passing over the weekend. And it's kind of a futuristic view in that they showed a position at NASA of a what we would now call planetary defense officer, and this movie was made way back in 1979, almost 4 decades before this actually happened. But the leading theory on the demise of the dinosaurs, the end of the dinosaurs, was a impact of a large asteroid or comet. It's one of the 5 major mass extinctions that is in the fossil record. And the evidence has been piling up over the last few decades that this is indeed probably what occurred. There is a layer of enriched soil, enriched in iridium around the world. And the most likely source of that iridium layer is from a large asteroid impacting the Earth. That was hypothesized and demonstrated by the Alvarez team back in the 1980s, and then this large crater was evidence of it was actually collected in the 60s and 70s, but it wasn't realized until the late 80s and 90s that this really was a crater now called Chicxulub crater off the Yucatan Peninsula in the Gulf of Mexico, crater 150 kilometers across. And that would be caused by an impactor the size of 5 to 10 kilometers in size. And the amount of energy released from that would just be incredible. This is a gravity map showing the existence of that crater. Of course, it's all submerged and covered over by many layers now. But that photo on the right side is me in the basement of the Smithsonian here in Washington, D.C., where they have one of the world's largest meteorite collections. And this, what I'm holding in my hand, it looks like a chocolate layer cake, is actually a sample of that region of the Earth's surface. where this iridium layer is, and that lighter layer that I'm pointing at with my finger is that iridium layer. So there's strong evidence that this led to the demise of the dinosaurs. There's also a lot of evidence around the world of craters on Earth. There's more than 190 confirmed impact structures. That means they've actually been surveyed, samples have been taken, and proven that these were created by an impact shock. They have all kinds of ages, all kinds of sizes of craters, some examples here. And of course, more recently, in Tunguska, Russia in 1908, not a crater, but over 2,000 square kilometers of forest was devastated by what was thought to be about a 40-meter sized impactor. It didn't actually strike the surface, but detonated several kilometers above the surface, causing a incredible air blast that created this devastation. So impacts, large impacts are very rare events, but can have significant effects. This is a meteor crater here in the US and in Arizona, one of the best preserved craters in the world. The impact occurred some 50,000 years ago by only a 50-meter sized asteroid, but it released energy equivalent to about 5 megatons TNT, and the crater is a little over a mile in size. But the devastation from the blast of this event would have caused catastrophic devastation out to 25, 30 kilometers from the site if it happened in modern day Arizona. So what's the risk here? This is a chart that appears in a lot of literature on this, about different sizes of asteroids and what their effects could be, the amount of energy released, and this average time interval in years between these impacts. So you can see that the smaller the object is, of course, the more frequent, the more there are, and so the more frequently the Earth gets impacted. And to get up to areas of regional scale devastation, 100-meter or so sized object, that happens only, every few tens of thousands of years. But I think a chart like this is somewhat misleading and gets misinterpreted because people say, well, the last one happened, 50,000 years ago, and so either we're due for another one or we're not due for another one, depending on your perspective on it. But it's an entirely random event. These don't happen at any regular intervals. The risk is entirely, when it can happen, is entirely random. And it's not like, and it can happen anywhere in the world. So it's not like the risk of getting hit by a hurricane, which only happens half of the year and only in certain parts of the world. This is something that could actually happen at any time, any place. So these kind of charts are a little misleading, I think. But what is valuable for this particular risk is that we can actually determine. We have now the technology and the ability to find these objects while they're still well out in space, long before the impacts, and determine when the next significant impact might occur. And so that's the job of the Planetary Defense Coordination Office at NASA, working with our colleagues around the world in other countries, space agencies, and astronomical institutions around the world. Planetary Defense Coordination Office was established over 4 years ago, and it is our job to manage all the planetary defense efforts across NASA and coordinate also with other U.S. government agencies and the international community to, first of all, determine if there is any significant impact threat aligned for us there in the future, be able to assess what the range of effects could be from that impact, i.e. How large is the object, when and where will it impact, and what those effects could be. And then develop strategies with our partners to mitigate those impact effects, be it it's a small object, so all we need to do is evacuate a small area around where the impact will occur, or a larger object, finding it far enough ahead of time that we have several years in which to mount the space mission to deflect it in space. So we're looking for what we call the near-Earth objects. Those are asteroids and comets that come into the inner solar system. This is the technical definition of a near-Earth object, but think of it as something whose orbit can bring it anywhere within about 30 million miles, 50 million kilometers of the Earth's orbit around the sun. And we're particularly looking for what we call the potentially hazardous objects. Those are the ones that come within about 5 million miles, or 7.5 million kilometers of Earth's orbit, kind of a torus around Earth's orbit around the sun. And those that are the size that could do significant damage, and the current threshold value we're using is anything that's 140 meters or larger in size, because object that size could devastate a statewide area. If you may have heard recently in the news about NASA's Cyberus-Rex asteroid sample return mission from the orbit, from the asteroid Bennu. This depicts the orbit of Bennu. It is a potentially hazardous asteroid, and in fact has about 1 in 2,700 chance of impacting the Earth in the latter part of the next century, 2175 to 2190 or so. But we can find these objects. Our current search programs are ground-based telescopes that we have mostly in the southwest of the United States or in Hawaii with our astronomical infrastructure there. And we have one space-based asset that we use. It's actually a repurposed astrophysics telescope that operates in the infrared part of the spectrum. Our guidance is from the White House. There was work done through our interagencies for development of a strategy and action plan for a viable response to a near-Earth object impact, getting ourselves in a better position to, first of all, detect these objects, and then figuring out what we could do about it. And it was released 2 years ago, but it's a culmination of about 4 years of work prior to that. So it started in the previous administration, and that document is available at that web link. We also do a lot of work internationally and with the United Nations Committee on Peaceful Uses of Outer Space. This is a continuing agenda item for that committee. And under the auspices of COPUOS, the member states have set up two entities to deal with this issue. The first is the International Asteroid Warning Network, whereby astronomers and observers and orbit modelers around the world participate for detecting and tracking and assessing any potential impact threat. And then the Space Missions Planning and Advisory Group is a form of the national space agencies to gather and work on technologies and techniques collaboratively for dealing with a possible threat while it's still in space, getting everybody on the what we call the same page. So how are we doing in finding these objects? This is our current discovery rate of these objects, and we're finding close to 2,500 a year now. we actually expect to considerably exceed that amount this year. These are near-Earth asteroids of all sizes discovered by these projects each year. As far as those that are much larger, 1 kilometer and larger in size, we have pretty well cleaned up that population now and found over 97% of those objects were found in the last decade, and now we're working on the smaller 100-meter or so size. We're only finding a few of a kilometer or more in size now, kilometer or two in size each year. So our cumulative discovery with NASA's having started a search program back in '98 we've just gone over 24,000 near-Earth asteroids of all sizes, of which almost 9,400 are 140 meters and larger, and almost 900 are a kilometer or so larger. And about a tenth of those objects are in potentially hazardous objects and potentially hazardous orbits, 2,100 which 156 are 1 kilometer or larger in size. And this goal of finding 140 meter and larger in size is actually directed to us, to NASA by Congress in what we call the George E. Brown Near-Earth Object Survey goal. George E. Brown was a senator, the chair, I'm sorry, of the House Science Committee back in the 90s. This population of 140 meter and larger asteroids is estimated to be about 25,000 in total numbers. About 4%, looking at the pie chart, about 4% of that population is a kilometer and larger in size, and we have virtually found all of that, or about 2/3 of the way of having found those 300 meters to 1 kilometer in size. So the real work to be done now is in this area that's smaller than 300 meters, of which we still have over half of those to be found. At our current rate of discovery of about 500 a year, it's going to take us some 30 years to find the rest of this population. So we're working on better capabilities to do that. And since we are a space agency, we can go to space to do this, which would allow us the capability to operate 24/7 continuously, not be affected by day-night cycles and the weather. And we can also hunt for them in the IR part of the spectrum, where they are much more prominent, stand out from the background of stars. And so this near-Earth object surveillance mission, NEAS Surveyor Observatory, would be able to find about 90% of that population within 10 years of operation. We can also, with the IR signature from these objects, make better estimates of their sizes, so we can immediately assess what their effects would be should they impact the Earth. We also operate 2 interplanetary radars. Now, you can't find these objects via radar. You have to find them optically and have a good enough orbit that you know where to point the radars to receive a signal return, and know when to expect that signal return, because you really got to dig it out of the noise to be able to know what it is that you're looking at. Otherwise, it just looks like radio noise. So NASA has its own Goldstone planetary radar in California, and then the large 300-meter dish in Puerto Rico, Arecibo Observatory. And with those capabilities, if the signal return is strong enough, we can actually radar image these objects and determine their more exact size and shape. It's a really odd rogues gallery of these objects. These particular objects here are all less than a kilometer in size, except for Tatatus, is a quite large near-Earth asteroid. We can also determine if they have their own little moons that orbit them, and about 5 to 10% of near-Earth asteroids do have these smaller asteroids that orbit them. Um, now, most people don't realize that asteroids are coming through the Earth-Moon system all the time. Luckily, most of these objects are quite small. I know you can't probably read this chart, but the numbers, it's more for impact of the numbers. In 2019, over 77 small asteroids came closer to the Earth than the Moon. 77 that we detected, and since we're only looking in the night sky, we know the number was probably larger than that, maybe twice that. But most of them are small enough, a few meters to tens of meters in size, that were they to impact the Earth, they would disintegrate in Earth's atmosphere and just create a large meteor, what we call a bolide. But there are a few that were of significant size, 60 to 120 meters in size. This object, 2019 OK, came within 2/10 of the distance to the Moon. In other words, about 40,000 miles of the Moon, and distance to the Moon. It's a little scary that an object this large approached the Earth, and we didn't actually see it until a day or two before because of the direction in which it came. And so we'd really like to be able to improve our capability to detect these things further out, so we have more time to do something about them, and that's what the Near-Earth Object Surveillance mission is all about. Another close approach that we know about, an example of having discovered an object well into the future, this asteroid Apophis, which will have a close approach with the Earth in April 2029. It's almost 350 meter sized object, so if it were to impact, it would do significant damage. But we know from our observations of its orbit that it's just going to be a close pass on April 13th, which happens to be a Friday the 13th, in 2029. It will pass closer than the geosynchronous satellites. And so it will be an event. This object is large enough that it will be visible to the naked eye. So we can all gather in the Mediterranean area for that evening on the April 13th to see this object pass by. But there are actual other objects, large objects that will become closer to us than the Moon over the next decade or so. One example is 2001 WN5. It won't come as close as Apophis. It'll only come about 2/3 of the distance to the Moon from the Earth. But this is an object that is as much as a kilometer in size. So that's another significant event that will occur actually in 2028, June of 2028. So let's talk about what we would do about object if it were detected to be on an impact trajectory with the Earth. Impact mitigation techniques. Well, we don't quite have this technology yet from the U.S. Enterprise from Star Trek. But we do have the technology that we think is viable that could be used to deflect these objects in space if we were to find them, able to find them far enough ahead of time, which we have the technology to do that now too. All you need to do is slightly change the orbital speed of the asteroid, just trim a few centimeters per second off its orbital velocity far enough ahead of time, several years ahead of time. And that will cause it to arrive either early or late at the point in space where the Earth is, and be a miss instead of a hit. And three technologies that we've studied for several years. In fact, this is from a report in 2010 from the U.S. National Research Council. Of technologies of a kinetic impactor, which is simply slamming a spacecraft into the asteroid and imparting a force on it, a gravity tractor, and of course the Hollywood solution, which is a nuclear explosive device. But these are all viable technologies that we have in hand that could be applied to this problem. We only have to find them first. The kinetic impactor is probably the most mature technology. As a matter of fact, we demonstrated the capability to do this back in 2005 with our deep impact mission and impacted a comet for scientific purposes to determine what it was made of. And it could be used if we have several years of warning, 5 to 10 years of warning. And then a gravity tractor, which is using nature's own tug rope, gravity, to gradually tug on the object. And that has advantages given enough time of a couple of decades because we can closely control what the new orbit is for the object. Well, let's talk about the Hollywood solution. We wouldn't do as they depicted it in Armageddon or even Deep Impact movies by trying to blow the object to smithereens. That would take a sizable nuclear device and sort of uncontrolled, or have a bunch of buckshot headed at us. Then it wouldn't change the direction. What we want to do is control and change the direction of the object, and we do that by having a standoff nuclear detonation, which irradiates the surface of the asteroid. It causes a blow off of material in one direction, and then the opposite reaction force would be used to change the speed of the asteroid. The gravity tractor, this uses the mass of a spacecraft station keeping beside the asteroid to slowly, with the gravitational interaction between the two over months to years, slowly change the direction of the asteroid. And we could enhance that mass of the spacecraft by going down and plucking a 10-ton boulder off the surface and gathering up in its arms, and then doing the station keeping maneuver. And then finally, the kinetic impactor, which, as I said, was the most mature technology. And in fact, we are now developing a mission to go demonstrate this technique. It's called the Double Asteroid Redirection Test, DART. It is now in its integration and testing at the Applied Physics Lab here in the United States. It is scheduled for launch late summer of 2021. Coming attractions here launching in summer of 2021, and the impact of the moon of the Didymos asteroid system will be in fall of 2022. And we're demonstrating this on a binary asteroid impacting the moon, because this way we're just changing the orbit of the moon about the primary and not changing the orbit of the system about the sun, so we don't impose any additional risk on the Earth being impacted by this asteroid by doing this demonstration. And so that's my pitch, and I'd be happy to then take any questions that folks have about this risk that we have of asteroid impact, and what we now, because we have a space program, can do about it.